today covering section 4.4 in the notes, and that's on special matrices. And in that we'll have banded matrices and symmetric positive definite matrices. So the first thing is banded matrices. So we want to talk about what does it mean for a matrix to be banded, and then also if we have a banded matrix, then how do we solve a system like that? So if we have an n by n matrix, A is said to have an upper bandwidth that we call P if Aij equals 0 whenever J minus I is greater than P. And so I'm going to do a small illustration for y'all to see what this means after I define the lower bandwidth. So a matrix A is said to have a lower bandwidth, which we call Q, if Aij equals 0, whenever I minus J is greater than Q. So if we look at, just look at maybe like a 4 by 4 matrix. So we have A11, A12, A13, A14. Alright, so here we have, so maybe we just have something like this. Or we have one super diagonal above the diagonal. So with the definition, we have J minus I is greater than P. Well, we can take a look at this. J minus I. So this has to be greater than P. So J minus I is 1. But we have an upper bandwidth of 1 here. J minus I greater than P. We have an upper bandwidth P if Aij equals 0. Oh, here, for these Aij's. So we look at the next row where, or the next super diagonal where we would have 0. So this index, the J would be 3, and then I would be 1. So that's always going to be greater than 1 here if I have a bandwidth, of upper bandwidth of just 1. Does that make sense, everybody? So anywhere I have zeros, this is going to be true for the upper diagonal part. Similarly with lower diagonal, so here we could say, let's look at like a different. Okay, so A12, A13, A23, and then A24 and A34. So this is the only 0 I have down here now. So I have 2 diagonals below the diagonal, so 2 subdiagonals. And the definition for Q was I minus J is always greater than Q. So this is the only one that we can look at here, right? Because it's the only one below the diagonal that's 0. the definition is if aij equals 0 whenever I minus j is greater than q. So here I would be 1, and j would be 4. I'm sorry, I messed up all of these indices over here. So that's 2, 1, that's 3, 1, and that would be 4, 1. Similarly, I was making a symmetric matrix. So that's 3, 2, and this one would be 4, 2. Okay, so now we look at I would be 4, and J is 1, so that's definitely, and here Q would be 2 to have 2 subdiagonals below diagonal, so 3 is greater than 2. So you can see we just count the number of diagonals below or the number of diagonals above.
The main diagonal.
The main diagonal, yes.
That will give you a bandwidth.
Well, that's going to give you your upper bandwidth and your lower bandwidth. For just the bandwidth, we define that as W equals P plus Q plus 1. So say we have a tridiagonal matrix here. Then P is 1, Q is 1, plus 1. So we have a total bandwidth of 3 for a tridiagonal matrix. So we just take our P and our Q and add 1 to get the total bandwidth. Okay, so are there any questions about finding the bandwidth? Do what?
Is P and Q 1 and 2?
Well, this, I was just looking at like 2 separate examples. So this is an example for an upper triangular matrix, and this is an example for a lower triangular matrix. But you don't have, you're not going to have like a P equals 1 and Q equals 2 or something like that.
So the bandwidth is basically how many diagonals you have on the matrix?
Yes. P plus Q plus 1. All right. So so any matrix, or any n by n matrix, A has a bandwidth of W is less than or equal to 2n minus 1. So every matrix is going to have a bandwidth of less than or equal to 2n minus 1. So if W is strictly less than 2n minus 1, then we have a banded system. So if it's equal, if W is equal to 2n minus 1, then we just have a regular full matrix. But if it's less than 2n minus 1, then we have a banded system where we have at least some of our diagonals are zeros. And so those are special cases that we look at. A more particular case that we want to look at is when we have a tridiagonal matrix and this tridiagonal matrix is of course P equals Q equals 1, total bandwidth, or W equals to 3. We want to look at this case because it's simpler to solve this type of system with Gaussian elimination. Forward and back substitution are also more efficient. So when we take a look at Gaussian elimination with the LU factor, a banded matrix with the LU factorization, we can say that if A has a lower bandwidth Q and A equals LU, is the LU decomposition without pivoting, then L has lower bandwidth Q. So if we are able to find the LU decomposition, and we've already seen that A has a lower bandwidth Q, then L also has a lower bandwidth Q. And similarly, if A has an upper bandwidth of P, and A equals LU is the LU decomposition. Again, without pivoting, then U also has an upper bandwidth. P. So this is just saying if we have A and it has a lower bandwidth or upper bandwidth, those are also the bandwidths for L and U in our LU decomposition. And the reason for that is here, when we do Gaussian elimination and we get L, then at most Q elements below the diagonal have to be updated, right? Because we don't have everything else below that is 0. And similarly, for this upper triangular matrix, if I have an upper bandwidth of P, then I only have to update P times above the diagonal because everything else above that is 0. So it follows that if A has O of 1 bandwidth, which is just 1 below, 1 above, then Gaussian elimination forward and back substitution only require O of n operations each. So that's a lot better than with regular Gaussian elimination, which is 2/3 n cubed, because when we take a look at the algorithm, it'll be easier to see why this is true too. So I guess, here, let's look at an example, and then we're going to take a look at the algorithm next, so we can see how this is true. So the example we have here is a matrix. It's a tridiagonal matrix, 5 by 5. So here's our matrix that we have, and then we can find the LU factorization of this. So the LU factorization. Okay, so there's our L's. Which would have A equals L, and then U. Okay, so after we perform Gaussian elimination on this matrix here, we get the matrices L and U. And so we can see that this tridiagonal matrix, we have a lower bandwidth one and an upper bandwidth one. So in L, we still have a lower bandwidth of 1, and in U, we still have an upper bandwidth of 1. So now let's take a look at the actual Gaussian elimination algorithm and why this happens. Let me read. So let's recall the Gaussian elimination algorithm. So we have 4J, 1 through n minus 1. So that loops over our columns, and then we loop over our rows through n. Does anybody remember what comes next in this algorithm? We need to compute, we need to find the multiplier first. So Aij over Ajj. And then what do we loop over next? So we've got 4k. And it's going to be j plus 1 through n as well. Yes. Aik equals Aik. And then what do we multiply by here? Ajk. Alright. So then we can just end all of these loops. Okay. So when we're going through Gaussian elimination, if I have a tridiagonal matrix, so I only have one lower diagonal and one upper diagonal, or one sub and one super. So if we're updating one row below the diagonal, which loop can be eliminated? Because if we're just doing this one row below the diagonal, then we don't need to keep going through all of the rows, right? We can just do an operation on this one row. Because a loop is going to go from this row to the next row to the next row, performing those operations, right? Okay. Well, with the tridiagonal matrix, we don't have to loop through all of those rows anymore. So which loop is the one that is going through the rows? Right, I. So we don't need to do this anymore. We only need, for the first one, I equals j plus 1. So instead of looping through all of those, we just do the operation where I equals j plus 1. So before we write our algorithm, so that takes care of the lower triangular portion. What about the upper triangular portion? When I eliminate something below the diagonal, then I have to update everything to the right of it, right? In every column. So which loop takes care of that? The K loop, right? So I don't need to update every column after that. Which column do I have to update? Just this first one. So just for K equals J plus 1. So now we can rewrite this algorithm. So we still have to loop over all of our columns at first. So we're still going to have 4J equals 1 through n minus 1. And we still have to find our multiplier. We still have to do this main step here. But when we find our multiplier, we're doing it for I equals J plus 1. And then when we get down to this step, we're doing it for K equals J plus 1. So we're just going to replace those indices. So we've got M J plus 1 J, and that's going to be equal to A J plus 1 J over A J J. And then now we need to do A I K. So what are the indices of this A right here, A I K? Well, right, so we would have J plus 1 for our column, but we already replaced.
So we're doing J plus 1, J plus 1.
It would be J plus 1, J plus 1 equals A J plus 1, J plus 1 minus M J plus 1 J A J plus 1. And that's it for Gaussian elimination with a tridiagonal matrix. So now you can see why this is just order n operations instead of 2/3 n cubed, because we only have one loop here. So remember, if you count the number of nested loops, that's going to give you your exponent for your order. All right. But there's one more thing that we want to look at here too, is the storage. So it's wasteful to store it in the traditional way, so we want to look at storing it in a different way. Now, let's see. Maybe I should do this now. Yeah. What I'm going to do is I'm going to make a 4x4 matrix here that I have, and it's going to be tridiagonal. Okay. Now I want to recognize which parts are the upper and which parts are the lower, like what would belong to U and what would belong to L. And if it's on the diagonal, then I'm just going to label it A. So instead of storing it in this matrix, we're just going to have a vector L and a vector U. So the way these are going to be labeled is A1, U1, and then we would have A2 here. This is L1, U2, L2, A2, no, sorry, A3, U3, and then L3, A4. So we just want to see which indices correspond to which of these, and then we're going to change up our algorithm based on storage, because we can just store this L and this U a lot easier than we can store a whole matrix. So let's see. If we take a look at, of course, anything that has the the same row and column index, then that's gonna be on the diagonal, so that will remain A. Now, anything where J is less than I is gonna be in U, and anything where I is less than J is gonna be in L, right? I'm sorry. I greater than J, because those were the same thing. So we just can take a look at our indices now, and I'm just going to replace them in this algorithm. Or maybe, would y'all rather me write it a new one down here? Okay. So let's do that. Try to write it smaller. So 4J equals 1 through n minus 1. Now, where is in J plus 1J? Is it in U, L, or A?
J plus 1 will be in L, right?
Yes, because I is greater than J. So we have, now we need to know which index this gets. It can either be J or J plus 1. So, L is always going to take the column index, and U takes the row index. So what is my column index here?
J.
J. Okay, and then A, J plus 1J, is that in U, L, or A?
It's also L, right?
Right. And so we take the column index, and then we divide by AJ. So, because that's on the diagonal, so we just take the same index. So that's going to give us our multiplier. And then for this step right here, this is on the diagonal, and this is on the diagonal. So it's just going to be A, J plus 1 equals A, J plus 1 minus, and where is this? In L or U?
Also in L.
Yes. And it would be LJ, so we take the column index. And what about this term?
That will be U, J.
Right, that would be U, J, because we take the row index there. Okay, and so that's all we have now for Gaussian elimination, and it's a more efficient implementation based on floating point operations that are involved, and also the storage that's involved too. So now we can see it's much easier to do Gaussian elimination on a tridiagonal matrix as opposed to a full matrix. Are there any excuse me, are there any questions about that at all? Okay. So now that we've looked at Gaussian elimination, let's just take a look at forward and back substitution as well. So now we can use these updated vectors to solve the system AX equals B using forward and back substitution. So those algorithms would be, so if we look at forward, we would say, first of all, we need to say y1 equals b1, and then we're just going to loop over. So I equals 2 up to n. And then we only have one step in here. So yi equals bi minus li minus 1, yi minus 1, and n. So this is all we have for forward substitution. It's the same forward substitution, but since we have zeros everywhere below the first subdiagonal, then we don't have all of the computations like we had before. And similar for back substitution, we're going to have xn equals yn over an, and then back substitution we look backwards, but we're going from n minus 1 to n minus 2 all the way up to n, and then the main step, yi minus ui xi plus 1 over that diagonal n. And so that's all we have for back substitution now. And so you can see again that each of these have order n floating point operations because there's only one loop in each one. So Gaussian elimination on a tridiagonal system not only saves in the LU factorization part, but also in forward and back substitution in terms of the number of floating point operations that we use. Because before, with a regular full matrix, we have order n squared for both of these forward and back substitution. So now we can see how this process is really simplified when we have a banded system or a tridiagonal system. So for a banded system, it would be a little bit more complicated than we have for tridiagonal because you would have more sub and super diagonals, but the same concepts still apply. You can still look at which computations must you do instead of going all the way down to n, eliminating elements below the diagonal, and all the way out to n, updating elements in the upper triangular portion. Are there any questions about any of this so far? Okay. So after Gaussian elimination, the components of the vector L are the subdiagonal entries of L and the LU decomposition of A, and the components of U are the super diagonal entries of U. So pivoting can cause difficulties for banded systems because it causes what we call fill-in. So when we pivot, we're going to disrupt our structure that we have, tridiagonal or whatever type of banded structure that we have. When I pivot 2 rows, it's going to fill in a non-zero where I once had a 0. So when pivoting is necessary, pivoting schemes that offer more flexibility than partial pivoting are what we typically use. So that's just something to look out for. Alright, so now that we've talked about banded systems, we're going to talk about a different type of matrix. And the type of matrix we're going to talk about now is called symmetric positive definite. Symmetric positive definite are matrices that we really like to use in numerical linear algebra, and they have some pretty important properties. First of all, obviously they're going to be symmetric, so that means A equals A transpose for any n by n matrix. So A equals A transpose for any n by n matrix. And we say that a matrix is symmetric positive definite if this is true, and for any non-zero vector x, then we have this also, x transpose ax is greater than 0. So that's the definition of a symmetric positive definite matrix. If my matrix is symmetric and for any non-zero vector x, then x transpose ax is greater than 0.
Can we not say that the Hessian is greater than 0? Like, are we not talking like a Hessian of a matrix?
No, not right now, but there are some other properties that may lead to that as well. So the first one, A, is non-singular. In fact, the determinant of A will always be positive, okay? The next one is all diagonal elements are positive. The largest element of the matrix lies on the diagonal. And lastly, all of the eigenvalues are positive. So these are all properties of a symmetric positive definite matrix. In general, it's not easy to determine if a matrix is symmetric positive definite. You can look at it and see if it's symmetric, but determining whether it fits all of these criteria is a little bit difficult. But one approach to check if a matrix is SPD, which is the abbreviation for symmetric positive definite, is to check the leading principal submatrices of A. Okay, so if I have a matrix AK and 1K, that's AK1, that's AK1, AK2, and then all the way up to AKK, we just check these leading principal submatrices. And so if it can be shown that that A is positive definite if the determinant of AK is greater than 0 for K equals 1 up to N. So if we can check all of these determinants and verify that they're greater than 0, then the matrix is also positive definite. So we want to check and see if it's symmetric first. And then this is one way that we can check all of these determinants. So one desirable property about a symmetric positive definite matrix is that Gaussian elimination can be performed without pivoting. And all of the pivot elements are positive. Furthermore, Gaussian elimination applied to these matrices is robust with respect to the accumulation of round-off error. However, since this matrix has special properties, Gaussian elimination isn't the most efficient or the most practical approach to solving systems of linear equations with SPD matrices. just in terms of number of floating point operations. So since it's not the most efficient, then we want to look at how do we solve a system that is symmetric, positive, definite. So that's what we're going to look at now. So what we call this factorization, so it's another matrix factorization. Is the Cholesky factorization. And so we define the Cholesky factorization as A equals G transpose, and G is going to be a lower triangular matrix. So G transpose is upper triangular. Lower triangular matrix, and it also has positive diagonal entries. So since A is factored into two matrices that are the transpose of each other, the process of computing Cholesky factorization requires about half as many operations as the LU factorization. So with the status, we really only have to find G, and then we already have G transpose. Whereas LU, we have to find L and U. So that's why it requires about half as many. And to be exact, it's 1/3 in Q floating point operations for the Cholesky factorization. So let's take a look at an example first. I think that would be best. Okay. So first of all, what I want to do is we're just going to take a look at how this algorithm is derived alongside while doing an example, and then we'll take a look at the actual algorithm. So let's look at a 4x4 example. This is a excuse me, this is a, no, that's okay. Alright, so if this is our A, then it's equal to G transpose, so these are G11. So that's G, and then we'll just have the transpose of this one, so G transpose, so it's going to be G21, G31, G41, and 0, 2, 3, 2, 4, 2. Alright, so if we multiply this out and get what that's equal to, then it can help us to solve for all of these entries, all of these unknown entries in G, so G11 all the way through G44. So let's go ahead and multiply this out. I need a good bit of space for that. Alright, so we get G11 squared G21, G11. I'm gonna make these further apart actually, because the further we go down, the longer the terms are gonna get. Okay, so that's our first row. And then we have G21 squared. G22 squared, right? Plus. And then we've got G21, G31, plus G22, G32, and then G21, let's see, you can't read wrong handwriting. So this row, this column, so G21, G41, plus G22, G42, and then G31, G11, G31, G21, G22, G31 squared, plus G32 squared, G33 squared. And so you can kind of see a pattern emerging. Let's see. What's going to be this row times 2, 3, 2, 2, and then 4, G31, 41, G32, 42, 33, 43, and then lastly, G41, 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 21, 42, 22, and then 41, 31, 42, 32, 43, 33, and then the last entry, 41 squared, 42 squared, 43 squared, and 44 squared. Okay, so this is kind of a tedious process, all of this, figuring out which what all of these are equal to, but we'll take it column by column, and let me move over to this one.
Why isn't that only at the lower part?
Because that's all we're going to look at. Because G equals G transpose, so if we find the lower part, then we have G transpose as well. And when we look at this, like when we solve for all these G11 all the way up to G44, we're going to do it in a way that's slightly different than what you would naturally do, but it's a way that leads up to the algorithm. Okay, so let's look at the first column. So we have G11 equals the, I'm sorry, let me look through this first. A11 equals G11 squared, A21, column, and then we look at the, so we're only looking at the lower diagonal part, or the lower triangular part. So we start at A22 in the second column, G21 squared, A32, G31, G21, plus G42, no, G32, G22, and A42, G41, G21, plus G42, G22, and then we have A33, so it's another diagonal. If you'll notice, the diagonal elements are all getting squared like this. And then 4, 3, 4, 1, 3, 1, 4, 2, 3, 2, 4, 3, 3, 3. Alright. Okay, so now we're going to use this to help us solve for all of these g's, these unknown g's, and come up with an algorithm at the same time. So let's look at the first column here. So A11, G11 is just the square root of A11. So now I want to work an example alongside this, so I can actually compute the g's for a given symmetric positive definite matrix. So the example from the notes, hopefully this is far enough over. 3, 9, negative 3, 17, negative 1, negative 7, 3, negative 1, 17, 15, 9, negative 7, 16, and 44. Alright, so now we'll compute each of these. So we've got the square root of 9 equals 3. The next one that we want to find is G21, which is just A21 over G11. So that's going to be negative 3 over 3, which is negative 1. G31 is next. And then we just say A31 over G11. So this is 3 over 3, which is 1. And then G41 is A41 over G11. So 9 over 3 equals 3. So now we've found the first column of our matrix G. Now, the way that we're, before we go on to the next column, you see that we have, when we're solving for, so here we solve for G41, this one is going to give us G22, because we already have G21. We're going to have subtractions, and then eventually we're going to also have divisions that we have to do as well. So we're going to take care of the subtractions in one column first. And that's the way the algorithm will work. So we can do all of our subtracting at one time. So we're going to take care of the subtraction like from the first column that contributes to all of the other entries of A. And then we'll do subtractions. And then I'll work through it nicely. Okay, so now we're just kind of updating A. We're not finding our G values yet. We're updating A in such a way that makes sense with the algorithm. So we have A22 equals A22 minus B21 squared. So we're just taking care of all of the subtractions in column 1. A22. Yeah, so we're just, but this is setting up to solve for G22, okay?
A22
Should it be G2?
G22 equals.
Yeah.
No,
Sorry.
no.
Wait, which?
Like, I know
Right.
talking about G2 equals
No.
A22 minus
Okay.
G. That's how it works.
No. What we have here is I'm setting up to be able to solve for G22. But I'm just gonna update A because see when we solve for G22 we have to subtract off G21 squared, right? So I'm not fully solving this for G22 yet. I'm just subtracting off. So like I'm updating A.
Oh, so G22
So
squared.
A22 is gonna become A22 minus G21, yes, squared. Does that make sense? So this is how the algorithm actually works. Alright,
So you're gonna make A22 equals that first, and then
then,
square root it.
right, after we do all of
eventually
this,
solve it.
yes.
Right.
Okay, I think we've only got about 15 minutes left, so I'm gonna try to go through this example quickly so I can get the algorithm written down too. But I think we'll get it done in 15 minutes. So this is going to be, y'all can follow along in the notes too, but I'm just going to write what these are going to be equal to. So this one is 16, and then we have A32, so we're updating A32 by subtracting whatever is in the first column here. So, but only the subtractions in the first column. So that one gives 0. Then A42 gets updated by subtracting whatever is in the first column there. Okay. And then we move to the next column, so this was updating this was for the first column, second column. Now we'll move on to the third column, and again we're just subtracting off whatever is in the first column. So A33 minus B31 squared, so 16. A43 is A43 minus G41, G31, which is 12, and then A44 gets updated by subtracting off G41 squared, which is 35. Okay? So now that we've subtracted off everything that's in the first column, we're going to actually solve for all of the elements in the second column. Because in the second column, we only have to worry about subtracting things in the first column. So we're ready to solve for those now. Does that make sense? Because these all deal, those three all deal, these three all deal with the second column, so we only have to subtract off things in the first column. Now these two deal with the third column, so we have to subtract off things in the first and second column. So we have to deal with the second column next to be able to solve for those. And lastly, we have to deal with the first, second, and third column here. But we're ready for the second column. Alright. So we get that G22 is just the square root of A22 because we've already subtracted everything off. So now we just need to take the square root, which is 4. G32 is A32 divided G22, which is 0 over 4. Oh, I forgot to move the computer back. We just saw that G22 is square root of 16, which is 4, and G32, which is A32 over G22, is 0 over 4. And then we have G42, it's going to be A42 over G22, negative 4 over 4, which is 1. So now we took care of the second column. Now we need to subtract off everything that affects the second column for all of A. So, or we remove the contributions from G's second column to the remaining entries of A. Alright, so.
How do you get G22 for the G32 part? How did you divide by that?
Wait, which part?
G32 equals A32 over G22.
Okay, let's take a look back over here. So G32 is right here. So we've already subtracted off here, okay. And then so we just have to take our updated A32 and divide by G22. Alright. So now we're gonna update column 3 based on whatever subtractions we had to do in column 2. So this is A33 is A33 minus G32 squared is equal to 16. Then A43 is A43. And so remember, we're using the updated values, so these A's now no longer necessarily what's in the matrix.
You wrote A42 equals minus G41, G21 equals 0 for the first,
where at?
G42.
I'm sorry, I'm wrong. G42?
Yeah.
Equals A42 divided by G22.
What's A42? Is it
A42
0?
is this updated A42. We found that somewhere.
Yeah.
Oh, yeah, it is. A42 in the notes is negative 4. And then, let me see. A42, A42 is, I'm sorry, I think I wrote the wrong thing here. This one is not 0.
It's negative 4.
It's negative 4, yeah. So, for the viewers at home, A42 here is not 0, it's negative 4. So that makes this work out over here now. We have A42 equals negative 4 divided by 4. So A43, okay, is going to be updated by subtracting G42, G32, which gives 12. And then A44 is updated by subtracting off G42 squared, which gives 34. Okay, so now this is, okay, we saw these here, but these are just the updated entries of A. So now I'm ready to find everything in the third column because I only had to subtract off things from the first and second column. So I'm ready to find G32, G33. That should be, yeah, we're ready to find G33, and it is the square root of A33, which is 4, and then G43 is A43 divided by that diagonal element. So you can see that we're always dividing by the diagonal element on that column.
3.
Yeah, 3. Okay, so now we've solved for these here. we only have to update A44 one more time, and then we can finally solve for G44. So A44, we're going to subtract off whatever's in that third column, which is G43 yes, G43 squared, and that gives 25. So now I can finally solve for G44, which is the square root of A44, which is 5. So now I solve for that as well. 0 minutes. Okay. So let's move to the other board. Now we actually have G. I don't need to erase that. Since we have G, we also have G transpose. So we've got 3, negative 1, 4, 0, 1, 0, 4, 0, 3, negative 1, 3, 5. And then G transpose, we just take the transpose of this matrix. So that's going to be G transpose, and so this is equal to A here, and then we can, so now we have the factorization of this matrix. So I think we've only got about 5 minutes left, so I'm just going to, I did it again. Did y'all notice that I didn't move it? Okay. Oh, man. Alright. So, all we did here was just fill in G and G transpose in these matrices by what we've already found all of these elements to be. So now I'm going to write down the algorithm for Cholesky factorization. Let me find it in my notes. Okay. So if we start in the first column and we loop over all the columns, then the first thing that we're going to do is take the square root of each of these diagonal elements, and then we're going to loop over the rows. So 4i equals j plus 1 through n. And then we're going to do the division next, so aij over gjj. A equals j plus 1 through n. And now we're going to do our subtracting off. So when it subtracts this off, it's doing it for the next round, kind of like we were doing in the example. So aik is aik minus gij gkj. And then we can end all of our loops. So what we have here is actually an outer product where we have A equals A minus GJ transpose. This main step of Cholesky factorization can be defined by this right here. Now there's an example in the notes. I guess we can take a look at it really quick. That shows where Cholesky factorization breaks down. Let me find it.
Well, if GJ equals 0,
Well, yeah, also if we have a negative along the diagonal too.
Right.
Um,
You can't take the negative one, square root of a negative number.
right, exactly. Okay. Okay, so where the Cholesky factorization breaks down, say I have this matrix 4, 3, 3, 2.
Hey, on that, you have for table circles 1 to n, but in the notes it's to I.
Oh, I'm sorry, you're right. Thank you, Vivian. It does go to I. The reason it goes to I is because we don't want to update anything past the diagonal, so that's fine. Okay, so, if we start these computations here, we've got G11 equals the square root of A11, so we get 2. G21 is going to be, A21 over G11, which is 3 over 2, so that's okay. A22 is, so then we update A22, G21 squared, so that's going to be negative 1/4. So when I go to compute G22 is where the problem comes in, and I'm trying to take the square root of A22. Square root of negative 1/4. So that's where we have the problem. Before I said you can check to see if the matrix is symmetric, positive, definite by checking the determinants, because of the expense of computing determinants, using the Cholesky factorization is actually another way, a better way to check to see if a matrix is symmetric, positive, definite, because if we have breakdown like this, then the matrix is not symmetric, positive, definite. Okay, so, are there any questions about anything else? Okay. I'll see y'all in lab